Let's learn about the basic operation of DC-DC converters and their characteristics by type. Why do we need DC-DC converters? For SMPS, which converts AC 100 to 220 volts from an AC outlet to DC in an AC-DC converter, usually only one DC voltage is obtained. However, since electronic products require various DC voltages for microcomputers, LED lights, motors, etc., a DC-DC converter that converts the SMPS output voltage, 24 volts, into various voltages of 3.3, 5, and 12 volts is required to create each DC voltage required. The high AC voltage of 100 to 220 volts is converted into a DC voltage of 24 volts by an AC-DC converter called a switching mode power supply, or SMPS. This is used as input to generate a low DC voltage of 5 volts in a DC-DC converter such as an LDO, series regulator, or switching regulator. There are various types of DC-DC converters depending on the load or input-output voltage conditions. Let's look at the characteristics of DC-DC converters by type. DC-DC converters are divided into two types: linear regulators and switching regulators, depending on the conversion method. Linear regulators are classified into two types: series regulators and LDOs, and are called linear regulators because the relationship between input and output operates linearly. A series regulator is a regulator in which the control device is configured in series between the input and output. Since the control device is in a series structure, it is called a series regulator. Since the input voltage is reduced to a lower voltage through the control device, if the difference between the input and output voltages is large, the loss in the element itself increases. Since it is a step-down method, the input voltage must be higher than the output. LDO is an abbreviation for low dropout. It is a linear regulator that operates even at low input-output potential differences, and its basic structure is the same as a series regulator. The input-output voltage difference of the series regulator is at least 2 volts, while the LDO has a characteristic of less than 1 volt. For example, if a 3.3 volt output voltage is required from a 5 volt input, the series regulator cannot generate 3.3 volts, so an LDO with a low input-output voltage difference is required. Switching regulators have different circuit structures depending on the relationship between the input and output voltages, and are divided into buck, boost, and buck-boost. In addition, there are various methods depending on the classification criteria or circuit structure. This method turns the DC input on and off through a switching element to produce an output voltage of the specified value. Depending on the circuit configuration, not only a voltage lower than the input voltage but also a voltage higher than it can be output, and it is also possible to obtain a negative voltage. The step-down method that generates a voltage lower than the input is called buck. The step-up method that generates a voltage higher than the input is called boost. And the method that generates a negative voltage is called buck-boost. In this way, switching regulators can obtain various output voltages and are more efficient than linear methods. Let's take a closer look at the series regulators and LDO in linear regulators. Let's take a look at the 7/8 series, which is a linear regulator that has been commonly used since the old days. 7805 is 5 volts, 7809 is 9 volts, and so on. The 78 series is a regulator that outputs a constant voltage, and the 79 series is a device that outputs a negative voltage. The pins of this device have 3 terminals: input, output, and ground. Looking at the internal circuit, it consists of a control device that controls the current passing from the input to the output side, and an error amplifier that compares the divided voltage of the feedback resistors R1 and R2 with the reference voltage V reference to linearly control the control device to obtain a constant output voltage. When the output voltage is low and the feedback voltage is low, the output of the error amplifier increases, which increases the passing current of the control device. And when the output voltage is high, the passing current is reduced to keep the output voltage constant. Since 1 or 2 NPN transistors are used as the control device between the input and the output, the voltage drop between the input and the output is approximately 2 volts. Therefore, in order to obtain a 3-volt output, a voltage of at least 5 volts must be input. LDO stands for Low Dropout Regulator and is an essential power supply component for mobile devices such as battery-operated products or cell phones where power efficiency is important. As the voltage difference between the input and output, i.e. the voltage drop, must be small. It has a structure similar to a series regulator, and by using a MOSFET with low voltage drop as a control device, it has a voltage drop characteristic of less than 1 volt. When the output voltage is low, the output of the error amplifier is lowered, which increases the passing current of the control device. On the other hand, when the output voltage is high, the passing current is reduced, so that a constant voltage is always output. Understanding the electrical behavior of inductors and capacitors is necessary to understand the operation of switching regulators. When the switch is turned on, the current gradually increases and flows through the inductor, and the energy of 1/2 Li squared is stored in the inductor element itself, that is, the current is charged. And when the switch is turned off, the current charged in the inductor flows to the load side and is discharged. Inductors charge and discharge current and have the characteristic of inertial current that continues to flow in the direction in which it was flowing. When the switch is turned on, the current flows into the capacitor, the voltage gradually increases, and the energy of 1/2 CV squared is stored in the capacitor element itself, that is, the voltage is charged. And when the switch is turned off, the voltage charged in the capacitor causes the current to flow to the load side and discharge. In other words, a capacitor has a voltage charging and discharging operation structure, and the capacitor performs a smoothing function through this voltage charging and discharging action. If we look at the operation of the buck, which is a step-down converter, when the switch is turned on, energy is stored in the inductor, and when the switch is turned off, the energy in the inductor is transferred to the output terminal. In other words, the input DC current is stored in the inductor through the switch, and when the switch is turned off, the energy stored in the inductor is transferred to the output terminal. At this time, the diode plays the role of creating a discharge path for the inductor. The buck converter is structured to transfer a portion of the DC input to the output, so it is possible to generate a voltage lower than the input voltage. The capacitor at the output stage acts as a smoothing device. If we look at the operation of the booster, which is a step-up converter, when the switch is turned on, energy is stored in the inductor, and when the switch is turned off, the energy stored in the inductor is transferred to the output terminal. In other words, the input DC current is stored in the inductor through the switch, and when the switch is turned off, the energy stored in the inductor is transferred to the output terminal. The diode plays the role of creating a discharge path for the inductor. Since it is a structure in which the energy stored in the inductor is discharged by superimposing the input voltage, the output terminal voltage can be a higher voltage output than the input. If we look at the operation of the buck-boost inverting converter, when the switch is on, energy is stored in the inductor, and when the switch is off, the energy stored in the inductor is discharged, causing the output current to flow in reverse, resulting in a negative voltage at the output. In other words, the input DC current is stored in the inductor through the switch, and when the switch is turned off, the energy stored in the inductor is discharged, causing the discharge current to flow in reverse, resulting in a negative voltage at the output. Since the inductor has the characteristic of inertial current that continues to flow in the original direction when discharged, the negative output of the buck-boost inverting converter is possible. In this way, the switching regulator can output various voltages such as step down, step up, and negative voltage depending on the configuration and arrangement of the inductor with current charging and discharging characteristics and the switching element that determines the charging and discharging path. Let's look at the pros and cons of two types of DC-DC converters, linear regulators and switching regulators. The output voltage is structured so that the linear type obtains the output by stepping down from the input, while the switching type can step down, step up, and invert. The output power is limited to a few watts or less for linear types, while the switching type can also output high power. Efficiency is low at less than 60% for linear type, and high at more than 80% for switching type. The noise is small for the linear type and large for the switching type due to switching noise. Response speed refers to how quickly output is produced after input is received, and linear types are fast. The linear type is simple to design because it only requires an external bypass capacitor, while the switching type is complex because it requires determining the inductor specifications. Therefore, the number of parts is more for the switching type and the circuit cost is more expensive than that of the linear type. Thank you. Bye.